Good morning. I hope you could enjoy the recorded lecture last week. Sorry for not being here. Um, anyway, today I'm going to talk about dynamic experiments, because that's also a side of doing experiments with imaging. And as usual, we have a lot of modules. I think most of them you know. There are some new ones here about feature detection and transforms, and the rest I think is just the usual stuff. Some books, we always come back to John Ross. Then there is a new one that would be interesting if you're going deeper into registration. That's a pretty good review over registration principles. And in the book by Bernd Jene, Spatial Temporal Image Processing, you also can get some ideas how to work with the time series of images. There is also a bunch of papers and sites, and that's in general. So for example, here we have some tutorials and registration guides which could be relevant if you want to implement these things. And let's go on. So until now in QBI we have been talking about a lot. We have, in the beginning, we did image enhancement to reduce the noise. Noise is actually a very important thing also when you start looking at time series, as we will see soon. Understanding histograms, automatic methods for segmentation and labeling, looking at individual shapes, also more complicated shapes, and looking at distributions between different materials. And all these are actually tools that we can use in the time series analysis. So in the end, you have to extract some information of these time series. Could be that you want to look at grains changing size or moving around or something like that, grains or cells or something. And with that, we come into a topic where we want to identify these between the different time frames. But all that, this material will come in as tools on the way for doing this. So we have been talking about now different things. We have looked at quantitative and imaging, but the big thing we haven't really touched yet. We have, of course, looked at volumes, that we have 3D data. That's kind of big. You can have a volume of, say, 20 gigabyte without a problem. But beyond that, we haven't really looked at big. So what we also mean by big is the variety. We touched that a little bit in last week's lecture, where we look at statistics. For doing a scientific experiment, we need to look at variations, changing different variables and see what comes out of it. Now in the last part, we have the velocity too. So we have something that is changing with time. And could be that it changes in a controlled manner. So you can do experiment 1, then you do something, then you do experiment 2, then do something. Or it could also be really acquisition as a time series. So with the big part in this lecture, it's not just that we have large amount of data, but it's actually being ready for having this big data. So that's actually more about coding strategies and building up frameworks, how you can work with it. And for that, we also, of course, need to be having methods that are scalable. So doing 1 or 2 shouldn't be much less difficult than doing a lot of examples. And for that, we need some kind of scripting, batching procedure that is easy to customize. And today we are mainly looking into the simulations and maybe some experiment design, how to create these time series data. And of course, we will have also talk about the motivation, why and how, and some scientific goals of these time series experiments. So we have different types of time dynamic experiments, or different aspects of it. One is that we actually have a dynamic process, and we want to relate objects in motion, or something in motion that changes with time, and we want to monitor and quantify these changes. Real time is a very fancy term. Many people say real time must be fast. Doesn't really have to, but it's actually about being able to sample the process with sufficiently many points, and that you get it in time. So in computing, there is a definition that input data should be processed within milliseconds, and it should be a virtually immediate feedback. But doesn't really have to be that when you're talking about the experiments. If you have a process that goes over years, you don't have to measure with millisecond precision. So then you're just sufficient to measure on that time scale. Then the last part is the imaging, where we have the capture, storage, manipulation, and display of the data. And all that together is what we are going to work with. There are different types of dynamic experiments, and you have to specify in the beginning, when you start planning your experiment, what kind you have. And first of all, we have the two types. One is continuous, something that you kick off and it happens, and then at some point it stops. Then we have the repetitive processes, something like these swings that goes back and forth. That is something you can use in the acquisition. And another example would be to have an engine which is rotating, it's always coming back to the same place, doing the same thing. And that is something you can use also in the acquisition, because then you can have some trigger point and restart the acquisition and accumulate, and in that way you can get more counts on your detector, and with that improve the signal to noise ratio. That you can't do in the continuous case. Then you have to just hope that you sample fast enough and that you get the signal to noise ratio that you need. So, which kind of information are you looking for? First of all, how fast is something moving is quite natural. Could also be how many particles are present. For example, if you have a cell colony, with time, if you feed it, it starts growing, and then you can count how many cells there are on the disk at different times. Or if they maybe suffocate each other, they will maybe decrease. You can also check if the size is constant or if it's changing with time. Possibly if it's something that is moving. Are some of these cells moving faster or not? Are they rearranging according to some material in the images, or some for getting some good conditions? And these are things that you would maybe like to look for. And the image analysis, of course, is we need methods now to track objects between different points. Also possibly track the shape change, track distributions over time, possibly tracking the topology, maybe even tracking single voxels, but that is a little bit too detailed mostly, but it's more like groups. And we could also possibly look for deformation and strain in the samples. And well, your imagination's probably set stop for what to look for over time. And these are some things that we need to look into now. Well, actually, I'm more going to talk about how to prepare the images to extract the information. So, it is possible to look at things in 2D, but in 3D it's not so easy to visually at least assess what we have. Let's see if this works. No, I don't think so. Let's do it like that. So if you have this foam bubbling up, I think it was milk foam on a coffee cup, and you can see that bubbles, they are moving, they are growing sometimes, but it's not very easy to see this. So a lot of information is obscured in this field, so we need to have some really good analysis to extract the quantitative values. Also 2D images can be a problem. So what you see here is some water jet, and you can see some bubbles in it. I think this was a light image where you just show a lot of light, illuminate a tube from behind and then take a camera, and then you can see these bubbles. And this is a lot of data, and you need to find all these bubbles. And you can see some of them, they are not easy to track in this image. Another time series would be coffee making. This is a neutron image time series of 2D images where you can see how the water is boiled in this coffee pot. And this image is a kind of visualization how the water is moving from the lower part up into the prepared coffee, and you can see the bubbles. And things you could possibly quantify here would be, one is seeing the rate, how the water level is changing over time. So that one is probably not so difficult to see, except that there's a lot of bubbles in when it's boiling, and there is a lot of sprinkle in the top part. You can actually find this, that's a link to that movie. The other problem is also when we have creating our 3D images. So this is a tomography. There we actually, in principle, acquire a lot of images around the object, and then we can reconstruct a volume, and that is the 3D kind of data that we can produce. Here is mostly not so much about registration or time dependence, at least not when we do the single tomography. But for example, if you want to do monitoring of the heart, today it's actually possible to have scanners that can see how the heart is moving within the body. And there you have problems that patients are breathing, and you need to position the heart in the right way between the projections possibly. Another case that may be a bit tricky is when we have microscopy, do stage tilting to produce some depth information, but this is incomplete, and that also gives you some problems in the reconstruction of the data. So some scientific goals for for these dynamic experiments is rheology, understanding how water is or some liquid is moving around or mixing during the experiment. Could be blood moving around with or without tracer elements, oil going through some rock, and the airflow through some dough while baking bread. You can mostly not see the air, but you can see the bubbles forming in the dough. Another thing we also look at is the deformation. So we can look at how the is lysis a word? I think it's a typo, but okay. Red blood cells in an artificial heart wave valve, how they behave if they are worn down. We can see if there are microfractures in bone while it's growing, or stretch fractures, and can also look at toughening of different wood types, seeing what kind of what compression does to the wood while it's actually imaged on the same time. So with dynamic experiments, this is more the experimental planning. We have usually a limited field of view. We are limited by the voxel size, mostly. Also, which frame rate we can achieve, either in 2D or in 3D. There is also a dose limitation. Mostly when we want to do these experiments, we want to do it, say, with X-rays or laser light, and that can induce sample damage, so we may need to limit the flux in order to prevent the damage. And mostly there is some kind of non-zero cost for the experiment, and mostly you have to decide between the spatial resolution and the temporal resolution. Mostly you can't have both because you are, as I said, dose limited, not to damage the sample, or even your source doesn't provide more counts. So that this is always a trade-off you have to do. And things that affect the image quality is, of course, the speed of the process that we are looking at, the spatial resolution, and also the intensity dynamics. And all they are hanging together in different in the experiment, because you have limited flux, as you will see soon. And looking at this image, you can see that up here would be in this picture of some water flow. You can see up here, you can see nicely how the water is moving, maybe even some sprinkles. But when it starts moving faster over this edge, you see just a blur. And that actually shows us that in this case we can resolve nicely the cracks, but we can't see the full motion or the still frames of the water. So you would have needed a longer exposure time for this, shorter exposure time for this picture to really freeze the water. So let's have an example. We have a dose-limited experiment. We're starting out with 100 micron pixels. We have 1 second exposure time, and in this case I'm talking about neutrons, so we have with this about 800 neutrons per pixel. And now if you want to change, you see that this wasn't enough for seeing what you want to see. And if you want to maintain the signal-to-noise ratio and want smaller pixels, then the cost will be longer exposure time. And if you remember from lecture 2 or 3, the filtering and noise lecture, then you know that for most of these counting detectors or counting processes, you have a relation for the signal-to-noise ratio that you have to increase the exposure time or the pixel size by the square to get a doubled signal-to-noise ratio. So it's always very costly to change something. So if you want smaller pixels, then you have the longer exposure time. If you want higher frame rate, you have to increase the pixel size. So you have to balance these two against each other until you get the information or the images that you need. So what we can do is, for example, we want faster, so we can resample the image. Here I actually put somewhere, there was a vertical line, yeah. So you can actually do rebinning, so larger pixels. But if you do that, you will be able to capture the time dynamics, but you may miss small details in the images. So you have to choose between what you want to have. When you come to the frame rate, you have to work with some frame rate, and usually if you have something that rises in time like this, you should have at least 10 points on the rising part to get some good information. Maybe even more, depends on what kind of process you're studying. So this kind of bad sampling where you just have points that see what was before and what was after, but never what was between, doesn't really help you in this dynamic experiment. Then there are some experiments you can do a stop and go. So you run the experiment, let it stabilize, do your images, then you make the next step, let it stabilize, do that image, and then you can see stepwise what's happening. In some processes that is possible, others you can't do this. And in particular, if you want to really see what is happening between step 1 and 2, then you have to speed up and take the cost mostly of very noisy images. So when we plan this experiment, first of all, if we measure too fast, we may have sample damage. We may miss out on long-term changes because it produces so much data that we can't really capture everything. And you will also have noisy data. If you measure too slow, you will miss small and rapid changes in the data. And you may also get blurring artifacts. And that was we saw in this little small water flow that when it was too fast, then it was just a blur. If you have too high resolution, usually your field of view is too small, and you may not be able to track all parts of the process that you want to have. And then if you have too low spatial resolution, then of course you miss the details. So all of this can be put together in this triangle here, where you have the process speed versus frame rate, you have contrast versus noise, also the limitation, what you can do with the flux of your source, and then you also have feature size versus resolution. So this was the grain package we looked at 2 weeks ago, and this is another experiment I did, and in that experiment we more or less just we had some cubical packing of sand, and in the end I reduced everything to just have one measurement per cube, and that was good enough for that experiment. So you can do a very strong reduction in data sometimes not. Analyzing a trivial process, so one that's just moving up or down or something, where you have a very distinct front. That can be done. So first of all, we create some movie. So this is a time series. And this movie can be viewed upon as a 3-dimensional volume where you have X and Y and time. And the analysis then, we can say that if we want to watch something, so let's say this was a bouncing ball, then it's only moving up and down. And tracking it from image to image may be difficult, but instead, if we extract a frame or an image in this plane instead, so in the YT plane, then you can see that we nicely can see where this ball is bouncing. And then it's also easier to do the tracking. But this is only for the trivial processes where you have very well identified objects that are not moving too much in sideways. And but it's a commonly used approach to look at these data. So here's an example of capillary rise, where if you put some porous material, say a sugar cube, in liquid, you can see that the water is going, or the liquid is going up in the sugar cube. This is the process of capillary rise, and it's even described by Washburn's equation, at least in the initial phase. Then gravity plays in and it gets more complicated. But in principle, this rise can be described as a function of square root of time. And if you look at it, you can see how the water is going up. So in the beginning it's rising quickly, and then after a while it's getting slower. And from that we can now extract this YT frame, and you can see that there is a quick rise, and then it's going slowly toward convergence. If you want to look at how this is done, I have a tutorial on that, where you can see all the steps, how we extract the data points and afterwards do the fitting and everything. So if you are interested, you can take a look at that. But in the end, we would create this kind of straight line, more or less straight line. Sometimes it deviates, but that's more due to sample inhomogeneities. Then sometimes, so first of all, beam time or time at the instrument is expensive. So sometimes it makes sense to start doing some simulations to tune in which are the relevant parameters of the experiment. So with that, we can use it also for validation, seeing if the processing is working. And what we want to start with is we have all our workflow from the previous lectures. We want to get rid of noise. We want to find all the cells. We want to analyze them somehow. And that is all in the previous lectures. But we still only have very little data, maybe from just a previous experiment, or you want to prepare for it. So now we want to do our simulation. There are different ways how to work with these data, and we can split them into two principles. We have pixel or voxel based methods, which is a cross correlation, or actually DIC is digital image correlation, so it's also some kind of correlation based method. Can also look at adding some physics into this modeling of the analysis, and we can do some transformations, affine or non-rigid. And the other approach would be to look for key points, and that is what I'm going to show you soon. And first of all, just for playing with the simulation, we have this basic simulation where we have 8, well, it says circles, but it's actually squares, so it's single pixels. So we only have a black and white image, and we want to see some motion in it. And the motion we have is dx and dy is -1, so we are moving up to the upper left corner. So this is the moving process that we want to look at. So what we need to do for this analysis, first of all, we need to do some thresholding to identify where we have our dots, component labeling to identify the individuals, possibly do some shape analysis or distribution analysis, and then put all that into some data frame or table to handle it for further analysis. So this is what's happening here. We are creating this information for each region, and we get this nice table where we have the positions, area, and frame of the index of the frame. So if we plot all this, what we have in the table, this table was just in the first 5, so we only see frame index 0. But if we put all of them together in a single plot, it would look something like this, where we can see it nicely. We have the blue here is the initial frame, and then it's moving frame-wise. Here I didn't put colors on the individuals, but more on the frames. And the motion we have is the -1, -1. So we could describe it we want to describe this somehow. And there are different ways of doing this, and usually let's start with the simples and see what can work, and possibly you need to do something more advanced, but maybe not too specified, because then you generalize. So here is quite a strange claim that we have some multi-hypothesis testing with neural networks and so on. It may be too specific, and maybe you should try to take one step back and see if there is an alternative to that. So the easiest way is to track the nearest neighbor, and mostly makes sense actually. So we have 2 points, one in the first image and one in the second image, and then we look and compare for all points in the images and see which one is the closest, and that would be the most likely candidate for being the same. And we're doing that, we compute the distances between all these dots. So we have black dots, they are from frame 1, and the red dots are in frame 2. And you can see that some of them have pretty long distances, and they are not very likely to be the next candidate. And others, they are much closer, so let's rather go for those. In this case, it's a bit inconvenient actually, because we have this -1 relation, and they are equidistant. So in principle, you have the same distance from this one, that one, and the same distance to that one. Then we probably have to do some kind of decision if we have the same distance. And the decision here is just to take the first hit. In the end, we want something to have something that has a unique connection from each point in one image to the next. And if we would take the other one around, it would be confusing and it wouldn't end up in a good tracking. So here you can see the distances. There's square root of 2 and some other numbers. So you can see these are pretty clear that they are the shortest. So looking at this, we can also see the computation. So here we are looking at the neighbors of the individual points, and you can see how they compute these distances. And in the end, we have found our nearest neighbor points, and it points straight up in the left corner. And here we can continue tracking in all frames. So then we have to take the sequence one after the other. Another alternative to looking at these nearest neighbor for the tracking is to look at key points, and that is a way to reduce the load, because if we have many of these points and we want to compute the nearest neighbors for all of them, then we have quite a high computational task. So instead we can look at these key points and try to find which are the similar ones in our images. And for that we need a so-called corner detector, and one that is proposed as a first go-to is the Harris corner detector, which looks at a combination of gradients and information around the pixels. And so here we can see we have some raw image, and we see these corner features created by the Harris detector. And if we plot these points in the image, we see that they nicely hit the corners. This can also be tried on real images. A checkboard is not so, it's very synthetic, but in this case we can look at these cell images and it finds some corners, looks like actually pointy places produce corners. There is, for example, within this dot in the middle, actually also produces corners because it's also some object. But it gives us at least some points that we want to look at in the image. And with that we can do a better tracking, and it's actually quite stable, and the points, they are even insensitive to rotations, these corners. And with that we can see, yeah, there is a nice. So here you can see an example how the corners by the Harris detector, how they are actually nicely following, even though we are skewing and rotating and no, not translating in this case. It's just rotating and skewing. So they are nicely following, and that also makes it a good point to look at. So we have actually here, we have left the idea of identifying single objects by thresholding, but we're going directly on image features. And now that we have these corners, they are not identified. We could, of course, label them, that we have label 1, 2, 3, and so on these points. But that doesn't really tell much, because if we have two images and there is a skew, they can get new labels, and then we need to wait to connect them with each other. And that is to use these feature descriptors. There are different ones that are mentioned. One is orb, then there's one called fast, and one brief. And what it does is, in principle, looking for, it compares the central pixels to the neighborhood and produces a binary code for this. And this binary code looks something like this. So we have here different points and different bits of this code, and in this case it was 256 pixels that were compared in the neighborhood. And well, that produces quite some code to do this. I'm not going to go through much of that. But let's look at an example. We have now taken this cell image. We moved up, and we did y minus 15 and x plus 15. So there is a shift between these two images. And now we want to see what these descriptors can give us. And there we have the brief descriptor, which looks in the neighborhood and sets a 1 if the central pixel is less than some neighborhood pixel, and 0 if x is greater than the neighborhood pixel. And that gives us this coding. And with that, and the brief descriptor, we found some common points, and these will be used then for the registration. And some cases we didn't get relevant matches, or sometimes we get matches that don't really make sense. So for example, these two shouldn't be, while this one is quite a good match. So we have to do some kind of rejection based on how realistic the distance away these descriptors are. An alternative would be to use the orb, which is a bit more robust, and here you can see that it actually finds quite many points to begin with, and also that most of them actually are quite consistent, that the motion was going in, let's say it was going to the negative numbers. So this is actually flipped upside down. That's a bit confusing. So we have 500 up here and 500 down here. So it's rotated, or flipped actually. Another thing we want to look at is how to compute average flow, because when we have this time series data, we usually have too much data. And we want to do some kind of averaging to reduce it a bit, and we can do this both spatially and temporally, and of course spatio-temporally as a combination of the two. And we have some image where we produce this data frame and want to look at. And when we do the spatial averaging, we just do averaging within each individual time frame. So it's nothing between the frames. It can be used to reduce or to for filtering, if you want to do denoising. So this is one way, and The other way would be to create, if we have some field, as we have the x and y positions, we have some dx and dy in our field, and the field would look like something going downwards in this image. And it's very often when you have these vector fields that they are very noisy. We saw that a little bit also in the filter lecture when I looked at the structure tensor and orientation fields, that I had to do some averaging to get a good vector field, and this is the kind of averaging that would be doing. The temporarily averaging, goes between the frames, so we have looking at the same pixel from frame to frame and do averaging in that direction instead. And it's quite common that people are doing this moving average between different time frames in order to improve the signal to noise ratio and better see the trends in the data. And then with that we can also again we have our dx and dy, which are averaged out, and it gives us just a small, this is only for 1 point actually, some small averaging from time step to time step. The last one is actually doing both. So we do, in principle, this is a 3-dimensional filter of a 2D series. So we do, on one side, we have the spatial averaging, and on top of it, we also put the averaging along the timeline. And it's often needed because you have this noisy data, and you want really to get it in a better shape for your analysis. And one thing actually with these filtering techniques in the time frames is, what would I want to say? Yeah, in principle, you can apply normal filters. So seeing the 2D data as 3D, then you can just do a 3-dimensional filter, maybe with an asymmetric shape that you have, say, n by n in space and m in time. And with that, you can also tune how the filter is working. Here's an example where we have some moving cells, and you can see how they are moving. The vector field here is averaging for the different time steps in both time and space. And there we have a longer series that is a bit more complicated. So here the cells are moving stepwise up and down, up and sideways. And that of course gives us much more chaotic view. If there is noise in it, then you can see that the x and y, dx and dy, they are a bit flipping and flopping here. And also the vector fields are a bit crazy. And when we do the averaging, see if it starts. No, doesn't want to. Hey, no. I messed it up now. Sorry. Let's move on. Anyway, now that we do the temporal averaging here, we can see that we have x going up and down between 0 and -1, and y is moving a little bit more strangely. And our averaging of these vector fields turns into these arrows. And let's see if this one is working. Yeah. So here we get the vectors in the different time steps, how they are averaged out and cleaned up. Tracking is a very common task, and therefore also people have developed toolboxes for doing it. So here is one called TrackPy, and there is a lot of nice tutorials how you can do tracking of different use cases. So here they have their showcases how tracking is going to be done in using TrackPy. And if I remember right, there was pretty nice notebooks showing how to do this tracking for these different cases. This, for example, you can see this is some kind of foam that is moving, and you can see how the bubbles change their positions and shape with this vector field. So, and that's now let's take this one too. So, the problems with tracking is that we are often noise sensitive. It can be a problem that we have limited field of view, and that means that if you have things that are moving around, they may go out of the field of view and coming back again, and tracking that is not so easy. We can also have problems with the motion artifacts, and we can have problems that if you have working with cells, that one cell is dividing, which they should do, and then all of a sudden one object has become two, and the question is what to do with them. And that is where you have to put in more energy and into your analysis. And I believe actually that TrackPy can also handle these cases. So if you have that kind of data, you should take a look at that. So this I skip until after the break. So let's make some short break and continue afterwards.